All right. I will begin. Dear Father, we thank you for this day again. I thank you for this class and the students. Just ask you to help us use this time wisely to just review for the second test and just to answer any questions that remain, Lord. In your name I pray, Lord Jesus. Amen. All right, let's see if this thing works. Here we go. All right, well, guess we'll have class. Good. So here's the solution to mission 2. I'll just go through it quickly here. Problem 1, we had a box, mass 20 kilograms, rest on a floor with coefficient friction 0.7, kinetic friction 0.5. The question is, if we have F0 applied horizontally to the box, then what's the maximum force which can be applied without the box moving? So since the force of friction is less than or equal to that maximum value right there, which is 137.2 newtons, of course we need 0 acceleration. So that means that the force has to be less than that maximum amount. So our maximum force we can push on the box without it moving, 137.2. Let's see here. If we just give it a little nudge, what's the acceleration of the box? Well, if we nudge it a little bit, and then we're in the kinetic regime, and then the friction force drops down from that, right, to mu kmg, which I don't seem to have the number of, but oh, it is? Yeah, I know, but I don't know what mu kmg is. I guess it's 0.10, 98 newtons, I think, right? So 98 newtons. So 137 minus 98 divided by m is what you have. Although I guess I could put the F0 in there, I think. Yeah. Did I ever do that? Oh, yeah. Okay. So I guess I was writing my answer like that just in case somebody somehow got the first one wrong, but they still got the second one right. Then this would allow me to check their answer quickly. So anyway. Okay, so I get 1.96 meters per second squared in that case. So, just something to remember, the kinetic friction, typically less than the static friction. So there's this drop. All right. Here we have a car traveling on a flat circular track, 50 meters, coefficient of friction 0.9. I guess I should say mu sub s. I'm assuming that it's going without slipping, right? So that would be the static. I could put a mu sub s there. But on the flip side, at no point have I explained how to solve a problem where the car's wheels are slipping, right? So I wouldn't even know where to start there. Anyway, so so then the tangential acceleration would be 0 for the maximum speed, right? Because the acceleration's got two pieces, the tangential piece and the center-seeking piece. And obviously, the largest speed is going to happen when the tangential piece is 0, right? That maximizes what I can make the v. Does that make sense? Right? So when we have a equals to v squared over r, where's the acceleration coming from? It's coming from the friction force, which has got magnitude mu mg here. So I then solve that, and I get about 21 meters per second for my maximum velocity. Then here, at this particular time, we have a tangential acceleration of 2 meters per second squared. What's the maximum speed then? Well, then I have to go back and figure out from the equation up there that the acceleration, let's see here, at a particular time, the car is increasing. All right, so I don't know the speed v, but I do know that this is 2, and I also know that mu mg is what it is. So I solved that for v, and I got 20.72 meters per second. So the big idea here, of course, is that for something to go in circular motion, something has to make that happen, right? The things don't just go in circles for no reason, right? So I have a problem in this room. You guys in the back row are talking while I'm talking. That has to stop for the rest of the semester. No whispering in the last 2 rows. Thank you. Understood? Because I have a problem, and this is why I requested not to teach in this room. Last time I taught in this room, I had the same problem. And when I had the student evaluations at the end of the semester, they're full of people complaining, students always talking while professor's lecturing. I didn't hear it. I don't hear you guys talking, but everybody in front of you hears it, and it's very distracting. So, sorry to blow up at you all of a sudden like that, but I have to say something because I keep forgetting to say something, and it's a continual issue in here. I detest this room. Nobody talks like this to their friends in a smaller room. But once we get in a big room, people just start doing it. Not that you're talking, you're whispering, I get it. But anyway, so the next one here, we have a mass, 20 kilograms, pulled by a force of 100 newtons at an angle 50 degrees above the horizontal as pictured. Box accelerates at 2 meters per second squared. What's the coefficient of kinetic friction between the box and the floor? Let's see here. So we're not given the coefficient, are we? So we have to figure it out. So what do? We write down Newton's laws. So why is this 0? Can you guys tell me? Yeah, the box is still on the surface, right? If it was flying off the surface, then that acceleration could be non-zero. But at the same token, I'd have to explain like what angle it's going off and all kinds of other things that we haven't explained here. So we can rightly assume that the box is still on the surface. So the vertical acceleration has to be 0 since it's fixed there. But on the flip side, the vertical acceleration being 0 means that the normal force and the vertical component of the pulling force as well as gravity have to balance out in this way, right? So that makes the normal force work out to this, mg minus that. Let's see here. But I don't know. Let's see here. But what I did first was I solved 1, because I also know the acceleration is 2 meters per second, right? So since I know the acceleration is 2 meters per second, I can use that here. And the only thing I don't know here is the force of friction, but I can figure that out because the force of friction is equal to this minus ma. But I know this and I know that. So that gives me that the force of friction is 24.28. Now that still doesn't tell me what the coefficient of friction is, right? Because we get that actually from, let's see here. Because the force of friction, of course, is mu sub s, well, I guess mu sub k here, right? Mu sub k times the normal force. All right, so then the normal force is given down here from the y equation to be this, and whatever that works out to. Now we have everything we need, right? Because we know the magnitude of the force of friction, we know the normal force, so we can rightly calculate the coefficient of friction then, because we know the force of friction is the coefficient of friction times the normal force, so 0.20. So I can just keep going through the solutions, but if you want, I can answer questions. I know we don't have to just do this. I'll keep doing this if you guys have a question. But I didn't quite work this problem in class, right? So here, let me ask a slightly different question here for you guys. How could I make this problem different and still test the same concepts on the test? Yeah. Oh, that was not a hand raising. That was one of these things. So here, what's that? Put it on an inclined plane. Ooh. We could do that. I like that. Huh.
A lot of forces at play.
I'm not sure that changes anything, actually.
But you had a gravity pushing.
Is it still fixed in place? Are we letting it accelerate downward? Somehow we're applying these forces as it's moving? I mean, How about this? We have the same situation, but with friction. We could do that, right? We could throw into the mix the force of friction from M1 and M2.
And would it be static friction? Or?
Yeah, we could do static. Well, that's the thing, is it moving or not? So assuming that the coefficient of friction is the same between both boxes, then the question basically becomes whether or not the net force on both boxes is enough to overcome that friction. And if it was, then it'd be moving. But usually I just ask this question. Or there's another more simple way to modify it, which is what? Add a box. I've done that. That's true. That's one way we could do it. I could add a box and take away a force, right? So we just have a force pressing on one side. And I could have the force pressing on the left, or it could be pressing on the right, right? That's another possibility. We could even let the force press at an angle or something, right? So how can you write down all the formulas for all these different cases? On a note card. I guess if you write really, really small, but a better answer is I'm not going to write down all the formulas. I'm going to try to understand the concept so I can solve every contingency. That's the idea in here, not to memorize formulas, right? Anyway, this is what all the physics instructors say, and we are universally ignored. I know you want to find formulas and plug in numbers. I get it. So anyway, talking about the theory here, we just write down Newton's second law on the mass 2 and the mass 1, right? And the sum of the forces. So F2 is going that way. The contact force goes this way on M2. And on M1, the contact force from M2 goes that way. And F1 presses that way. That's why there's a minus here. And then usual thing with these problems is we added the equations, and that allowed us to find the acceleration. And then, of course, once you know the acceleration, you can put it back into either one to find the contact force. All right? If I do ask this question on the test, the typical mistake people make is they find the acceleration and then they forget to find the contact force. That happens a lot to students if I ask this question. Like, people forget to find everything. And I don't think it's because they can't. I think it's because they just forget. I mean, I think so. Anyway, I'm not a mind reader, so I'm not really sure, but this one here seems very scary until you realize we can just set the acceleration equal to 0 to find the terminal velocity, and so we can solve for VT, right? The other way to do it, oh, did I actually do this? Oh no. Oh no, did I? Oh, I did. So so I recommended not doing that to you guys when we talked about it before, I think, but yeah, the integral of this is that. And then you can let t go to, then make progress. You'd have to solve this for v. And then let t go to infinity to answer the, I recommend setting the acceleration equal to 0 to find the terminal velocity. I think this is a better path, yeah. As I said, sometimes rigor is not an option. This one here, we have got two objects connected by a light string that passes over a frictionless pulley. The incline's frictionless, mass 2 kilograms, 10 kilograms, 50 degrees. Find the tension in the string and the acceleration of the system. So what I do is I write down Newton's second law on both masses. So M1A, apparently I'm taking up to be positive. M1A is equal to T minus M1G because gravity goes down. That's it on M1. On M2, we've got the tension force going up that way. The acceleration is parallel to the plane. M2G is the part of gravity that's parallel to the plane, M2G sine theta rather. And then tension goes up, so there's a minus there. Nothing else. If we did have friction, what would the difference be? We'd add a what? Yeah, there'd have to be like, well, it depends on which direction the motion goes, right? If it's going down the plane, suppose it's going down the plane, I don't know, which one's more massive?
Would it really matter? On the plane? Yes. Well, what I mean is, once you calculate it, will we give you a negative?
Well, it matters because we have to make the friction go opposite the motion.
We want to just give you a negative force of friction if you choose one direction.
Yeah, but we don't have that. Like, that's not in the formula. The formula for friction is mu sub s mg. I mean, okay, fine, you could put plus f. Okay, I see. You're saying I could just put plus the force of friction with the understanding that it's going to be positive if it goes up or negative if it goes down?
Yeah.
Sure, we could do that, but yeah, I guess the question depends on how the question's asked, whether or not I need to put the sign in there or not. Fair enough. But let's see here. Well, the acceleration ends up being positive, so apparently the the system's going like this, right? So given that, the force of friction would be up the plane, right? Everything being as it is, which would make me go minus mu sub, let's say minus mu sub k, which one? m2g cosine theta, right? That would be the normal force. We had m minus mu sub k m2g. Sorry about that. I actually did. I distinctly remember turning off the sound on this thing. I don't know what happened. That's weird. Anyway, so. Anyway, any questions about this? What's another way you could solve this problem? If you didn't care about acceleration, what could we think about? Yeah, we could think about like energy methods, right? We could think about the potential energy for each, and we know that the kinetic energy plus the potential energy has to be held constant, right? If there's no friction, so we could use energy methods for this. That wouldn't be a good thing to do for this problem because we're asked about acceleration, right? If you're asked about acceleration, energy methods are no help. If you're asked a question about velocity or position, well then kinetic energy and potential energy might be helpful to you. All right, next up here. Here we got 2 blocks over a pulley. Sorry about this scan, it's not great, but that's the 30 degrees, the 53.1 degrees. Again, here's some free body diagrams partially drawn, and it gets us these 2 equations. We got to be careful to use the right angle for the right, for the right mass. And then we work it out. Let me go on to the energy stuff because, I don't really have much to say about this here. I think you guys are probably more comfortable with the force thing because we've now had it on the first test and now this test again, right? So I think hopefully you guys will do better on the force part this time around than last time, right? Because last time the force was just fresh right before the test. All right, so here we have calculate the work done by this variable force along a straight line. Now I gave you the parameterization of the line, 1 minus t for x and t for y, and 0 to 1 because that's my favorite kind of integration, one that goes from 0 to 1, So I put in my x, my dx is minus dt, my dy is dt. You can calculate like this. This is equivalent to the definition I wrote where we did, f of r of t dot dr dt. In some sense, you can cancel the dt's and just look at f dot dr, where dr has got a dx and a dy in it. If you think of it that way, good. Anyway, I got minus 0.5 for the straight line path. And when we use the quarter circle path, which I give you the parameterization x equals cosine t, y equals sine t for 0 to pi over 2. By the way, I don't expect you to learn how to parameterize paths in here. If I ask a work integral that requires, a parameterization, I will provide the parameterization in here. So I would ask the question in a similar way, unless, of course, it was a straight line. In that case, I do expect you to be able to parameterize a straight line. We have a trick for that. What was it? Remember? We do, if we want to go from P to Q, we do R of T is P plus T times Q minus P, right? That puts R of 0 being P and R of 1 being Q. We've done that somewhere. So, yeah. I think I'll be to a problem where that happens in a second here. Hold that thought. But yeah, if I find a marker. So the parameterization to go from point P to point Q, like so. So a typical point here, R of T. The formula is P plus T times Q minus P. Try that out. If we put T equals to 0, we get P, right? If we put T equals to 0, we get P. If we put T equals to 1, we get what? Q, right. And what's the velocity here? kind of silly. The velocity is q minus p, whatever that is. So this is a constant velocity path. It just goes from point P to point Q. And this, of course, is for 0 less than or equal to t, less than or equal to 1. So, woof. I'll tell you, that projector is much brighter than you realize. Let's see here. All right. Let me go on here. So the point of this problem was if we calculate the work along the straight line from this point to this point, I got, I think, minus 0.5 up there. But if I work on the work done by on the quarter circle, we get minus pi over 4. These are, of course, not equal, which illustrates the fact that this force is not path independent. Therefore, by all the theory we talked about, it's not conservative. All right. If it was conservative, there'd be a potential energy function, and we'd be able to calculate the work done from this point to this point simply by calculating minus the change in the potential energy. But we obviously can't do that because the work depends on the path, right? All right. Find the potential energy function here. So we've got x squared plus 1, y hat, z e to the minus z squared, z hat. So honestly, folks, when I have something like this, I just write down the answer, to be totally honest with you. Like, I integrate x squared plus 1, I get minus 1/3 x minus x. I have to put a minus, right? The integral of 1 is y, so that's why I put a minus y there. And this z e to the minus z squared, that's a u equals minus z squared substitution. I get a 1/2 e to the minus z squared. But this is what I'm trying to solve separately, right? I want this to be true, I want that to be true, I want that to be true. Whatever method you choose to calculate the potential energy in here, there have been like at least 3 different methods I've talked about. And there's another one in the notes which I would highly recommend you don't do. In the notes I talk about how to calculate the potential energy from integration, from doing a line integral. Like, this is not the way. But however you do it, once you've allegedly found your potential energy, take a half a minute and calculate the gradient of it. Make sure it actually worked, right? Like, here's an alternative problem that I usually ask on the test. Given u of x, y, z equals to x squared y z to the 10th minus cosine xy, it doesn't have to be this exactly. Find the force. This is a very typical test question. I asked something like this. I don't know if you had a homework problem like this. Did you? Maybe not. I don't know. Could we solve this problem? How do we solve this problem? We need to know what the force. If it's a conservative force, is what? Minus the gradient of the potential energy function. What does that mean? That means that we're looking at minus partial x of that. Minus partial z, y rather, of that. Minus partial z. I regret this formula. Well, anyway, it is what it is. All right. So the first partial derivative, we can calculate. What do we got? We got minus 2x y z to the 10th. The derivative of cosine is, well, the derivative of cosine is minus sine, so I get minus a minus is a plus, but notice there's another minus outside. There's 3 minuses. Right? 1 minus from the differentiation, 1 that's there, 1 that's here, a net of 3. So I get minus the sine of xy. Not done, because when we do the differentiation, we have to do the chain rule, right? So I still have to multiply by what? I'm going to write it down. partial x of the inside, okay? That's what has to go there. Next up here, we've got minus x squared z to the 10th minus the sine of xy, partial y this time of xy. And then over here, we just get minus 10 x squared y z to the power 9. So I've left the two pieces not finished yet. What are those silly partials equal to? Excuse me. What's that? This is equal to what? Y, right? So we pull out a y there. And this? Since we're just differentiating with respect to y holding x fixed, the x pulls out, we get partial y, which just leaves us a leftover x. But there it is, like, you know, that's the force that results from this potential energy. We just have to calculate the gradient and multiply by minus 1. So my larger point is that if I have, and I will have some problem on the test where I ask you to calculate potential energy for a force which is given, that certainly has to be a question on this test. I've spent 30% of our time on that, probably. You can check your answer, right? You just have to calculate the gradient and check that you get back to the force that you're given. Why did the cosine go away over there? So why is that, guys? There's no z in it, yeah. So the cosine term is constant with respect to z. No z dependence. So it differentiates to 0. Uh-huh. So this, I mean, I'm just trying to... do I take points off if you don't check your answer for the potential energy? Well, not usually, but I do if you get it wrong. So, you know. All right. So here we have a constant force. The potential for the constant force is simply given by this. You can calculate the gradient to check our answer. It works. Let's see here. Next up, we have a problem. Listen to me. We've got a mass which moves from 1 minus 2 to 4, 3. I can calculate the work done by a constant force. So here, constant force, we can use the force dot displacement formula, right? Because that's what it simplifies to, yeah.
What's the thing 45 joules? Is it meters?
Oh, yeah. I don't know what's wrong with me here. Yeah, that should be joule. I got it right there. I don't know what happened here. Oh, man. You should have told me this before I scanned it. I guess I need to go rescan it. I'll try to do that after class. But yeah, that should be joule. But do you guys understand? So why don't I have to integrate here? Why? Two reasons, right? One, it's a constant force. Two, it's a straight line. So for straight line, constant force, I can just take the force dot the displacement, and that gives me the work done. Same for part A and for part B. Now for part C, we've got a variable force, right? It depends on x and y like that. So I can't just take the force dot the displacement because I don't know which one would I use, right? There's infinitely many different forces at play as you go from one point to the other. Which force should I use? It changes, right? So we have to calculate the work properly, which is to calculate the line integral here. And so we put in this for x, that for y. We take the dot product with the velocity of this, which is 3,5. It's just like the one we wrote on the board. It's that kind of parameterization. And it works out to 100 joules, apparently. That's one way you could do it. The other way you could do it, which would probably be smarter, is to notice, hey, this is a conservative force. I can write down the potential energy function. The potential energy function is this minus 5x squared plus y squared. So the work done is minus the change in the potential energy, which is simply 125 minus 25, which is 100 joules, right? Which way is easier? I think using potential energy is almost always easier if it's possible. All right, that's part of the reason we talk about it. But sometimes you have no choice but to calculate the work done by doing the integral. Because sometimes the force is not conservative, right? So here, would the answers be different if the motion was not along a straight line? The answer is no, because this is a conservative force. It has path independence. I could have had a straight line from the initial point to the final point. I could have had a wacky curve that still had the same end point and starting point. It would still been the same. All right, moving on here. Oh, funny. So this time I gave you a potential energy function of x squared minus x to the fourth. I asked you to plot the energy diagram and comment on the stability of any critical points. So here I figured out that du dx is what I have there, 2x minus 4x cubed. I factored out the x, and that gave me a critical number of 0 or plus or minus 1 over root 2. So apparently, I mean, those are the critical numbers, right? The x-intercepts, the x-intercepts of the potential are likewise 0, minus 1, and 1. So that's what the graph looks like, something like this. And so there's my graph. I drew in some representative energy levels just to get a sense of what happens with different possibilities, right? If I've got an energy below the middle potential well, I'm like down here. So in this energy level 5, all of this motion is classically forbidden, right? Because you can't have negative kinetic energy to get in here. And so anyway, so that gives me corresponding, the corresponding Poincare plot or phase plane plot, velocity versus position, and I've color coded it. So like the purple or bluish one corresponds to this here, that guy, you know. So if you were given a little nudge close to this point, close to 0, what ends up happening is you kind of spiral, you just kind of orbit around that stable critical point, right? Because that's a potential well, so 0's stable equilibrium. On the other hand, minus 1 over root 2 and 1 over root 2, these are unstable equilibriums. You notice that if you start there and you're given a little nudge, you might go way off that way, you might go this way, and you might just keep going. Like there's no telling which way you're going to end up if you're given a little nudge from either this point or this point. These are unstable equilibrium. In terms of the phase plane diagram, the stable equilibriums are the ones that have little circles around them. The unstable ones are the ones that have like crosses through them. All right, that's how to see it from here. Up there, the potential well is a stable equilibrium. The top of the hill is unstable. The interesting thing, I think, is that our intuition about how, you know, like balls either roll off hills or don't roll out of valleys matches our intuition about this, right? Because that's just kind of a coincidence of the fact that the potential energy due to gravity is mgh, right? So that same idea, the height is corresponding to the potential energy due to gravity. The vertical axis here is not height, right? This is potential energy in this plot. But your intuition about how height behaves with respect to gravity is much the same for that plot. Okay, so move on here. Power is force dot velocity, so I got minus 41.3 watts for this this lovely force here and that velocity. That means that the velocity and the force are in opposite directions, right? They're not directly opposite, but they're more opposite than they are parallel, right? If the power is negative, then that force is slowing down the motion, right? It's trying to slow down the motion. I don't actually know that it is slowing down the motion unless I know like the totality of the forces. If that's the net, is that the net force? I don't think I said that. Right? Yeah. Did I, let's see here. I said, what is the work done by the net force on M? Can we figure that out? We can figure that out because I told you the velocity is a function of time right there, didn't I? Well, I told you it's a constant velocity. What does that mean? What's the change in kinetic energy for a constant velocity? 0. That means the net work done is 0. So if the work done by this force is not 0, then we know that there's another force involved, right? So there's another force involved besides the given constant force, obviously. Anyway, the work done by this, you notice, so if we know the power developed by a force, to calculate the work done by that force, we simply integrate the power. Because that's what the work integral works out to be. We derived that like last class, I guess. But so anyway, that integrates to minus 82.6 joules. So apparently, if the motion is as given, well, I didn't even ask the more complicated question, which would have been a what? Like, what other force, what's the sum of the other forces involved here, right? That would be, that would be hard to answer in the abstract unless we had more information. Like, if I told you that there's another constant force involved here, what is it? You could figure that out much like we did last class. On the other hand, if it was a variable force, all I really know for sure is that the net work that the other forces do must be 82.6 joules, right? Because the work done by the given force and the work done by the mystery forces would have to balance out. That's all I can really say at this level. All right. When does the work energy theorem, when is it true? Like, for which force does the work energy theorem apply? Conservative? Nope. Doesn't have to be. The work energy theorem states that the work done is the change in the kinetic energy. This is true for which force? With respect to a system, we have to be talking about the net force. The net force is the one for which the work is equal to the change in kinetic energy. The reason for that is that that result is derived from assuming F is equal to ma. F is only equal to ma for the net force, right? If we're just talking about one of many forces, the force is not equal to the mass times the acceleration, right? It's the net force, which is the mass times the acceleration. Okay, so how about this one here? I guess this is another calculate the potential energy problem. This one, I probably could have also guessed the answer here, but I decided I should write you a solution which goes through that thought process in case you're not where you need to be to guess yet. This is how we do it. We integrate the first one. That gives me c1 of yz. I plug it. I plug it into this one. So differentiating 1 gives me this equals to that. This right here is that. This, when I differentiate 0, derivative of x, partial c partial y is the c1 piece. Aha, so that gives me equation star. I can integrate star with respect to y to obtain c1 is minus 3/4 y to the 4th plus c2, which is possibly a function of z. Remember, c1 could have had a z dependence. All right. So then I plug that into my number 1, which gets me to here. All right, so I've got the x part, I've got the y part. I still don't quite have the z dependence pinned down. So I plug that into my third condition, which is that I have to match the minus 6z there. The minus is gone because, remember, it's minus the gradient. That's why the minus is not here. So when I plug that in, that implies that dc2 dz must be 6z, which gives me, integrating, gives me 3z squared. So put it all together, and that's it. Of course, you could add a constant here, right? I could say plus 10, plus 47, whatever. And how do I know that I'm right? Well, hopefully I did the calculus right, but suppose I had doubts, Maybe you let a friend do it, and you know that friend. So you need to check the work, right? We all have a friend like this. Mine's name is Crazy Paul. But if we take the gradient of this, we get, minus 3x squared minus 3y to the cube, minus 3y cubed, comma, 6z. Then I have to multiply that by minus, and that gets me back to there. So, yay, it works. It works. Once I know the potential energy, I can calculate the work done, right? So, it's important to know that and be ready to use it, right? We've talked about another way to calculate the work done along a line segment from 123 to minus 2404, right? We could also use the formula I've mostly not erased on the board over there, right? And that we find the parameterization going from one point to the other, and we could actually go back to the definition of work done. But that would be the wrong way to calculate this, because we have the potential energy. When we have the potential energy, we should use it to calculate the work done if that's what's appropriate, if our force is in fact conservative, and this one is. So I calculate minus the change in potential, which means that I take u of 1, 2, 3, and I subtract u of that. And to do those, I just have to plug these numbers into the formula, right? And be careful with the parentheses. Don't forget to distribute the minus. It's a popular mistake in these kind of things, but whew, yowzers. Minus 42. I'm sure that's an accident. So it's a conservative force, so the integral around a loop is 0. That was another thing we have talked about a bit. 30 kilogram grate is lifted by a constant force at a constant velocity from the ground to a shelf 1.2 meters above the ground. So the work is F naught times delta y. They're both in the same direction, so it's a positive work, right? In contrast, the work done by gravity is negative because the gravity is opposite the direction of motion, right? If I go down here and up, then gravity's down, but my motion's up, so gravity's doing negative work. How do I know that the net force, the net work is 0? That's because I was given constant velocity, right? If it wasn't constant velocity, then I wouldn't have known that the lifting force was mg, right? What if it wasn't at constant velocity? What if I lift the box such that, at the top of the, I was thinking of taking this whole stack of homeworks and illustrating it like this, If I lift the stack of homeworks and at the top now I'm playing with fire. But, if I'm lifting like that, then at the top of my lifting, it's not with constant velocity, right? I mean, it starts at 0, right? Oh, I'm going to stop. You've all stapled, right? Yeah, I think we would have been fine. We would have been fine. If I tried to do this on mission 1, it wouldn't have went well. But, Anyway, my point is, if your velocity is not constant, then the change in kinetic energy is not 0. And we couldn't just assume the acceleration is 0. I'd actually have to give you more information to figure out what the lifting force was. If the change in y is the same, the work done by gravity is always the same. Gravity doesn't care about the velocity, right? Gravity is just, mg delta y there, like that. All right, anyway, moving on here. This one here, 2 tugboats pull on a disabled supertanker. So this is just a net force, calculate, we're trying to calculate the net force, right? The total work we can calculate from the net force, and that's what I do here. Of course, actually, well, there's 2 different, so that's, okay, this actually brings up a good point. I calculated this problem by calculating the work done by each tugboat separately and adding them. Another way you could have done this would have been to find the net force by adding those forces, and then calculate the work done by the net force. We would have got the same answer. And this corresponds to a principle of physics which is called superposition. The work done by the net force is the sum of the works done by all of the constituent forces. So if I've got 10 forces making up the net force, I can calculate the work done by each one separately, to find out the work done. That's important because sometimes our net force is not conservative, but maybe part of it is. So for the part of the force which is conservative, I can calculate the work done by minus the change in potential energy, and I can calculate the work done by friction according to a different rule, right? We know work done by friction is going to be negative, I think, usually. All right. Let's see here. Let you guys look at that. I was going to say, I wanted to talk about this for a second. This problem doesn't belong. This is just a, hey, I'm helping you guys review for the final exam problem. This is a test 1 question. I don't know what this is doing in here, but I left it. Because you don't really, that's a test one question. This one is, make sure you study this one. I do often have questions about inclined plane and spring. That's not unusual. I like this one a lot. This is a nice problem, I think. We talked a lot about this earlier this week. I don't really have much to say here. Let me show you one thing, and we'll stop here. I just wanted to show you a problem. Here's a page from like last year's test. All right. So, number one, I had a box sliding down an incline and it compresses a spring. I asked, I think I gave it, trying to remember. Oh, I asked what the maximum speed of the mass was during the motion. So that'd be the mass, that'd be the velocity right as it gets to the bottom of the incline. And then I asked what the spring constant was. So there's this, let me make it bigger for you guys. So I think that's a nice problem. All right, so you look at that. And then this one is kind of more relevant. This is kind of what I was just talking about. Here I gave you a horizontal force, which is given, and also the friction force. And they act on a mass that moves from rest from that point to that point along a path of length 25 meters in the xy plane. Find the speed of m when it reaches 1, 2. So to do this, you need to use a mixture of two things, which is that the work done by friction is the length of the path times the friction force with a minus, right? It does negative work. And also to calculate the work done by that force, well, that's a conservative force. It has to be given the problem. If I ask you to calculate the work done by a force and I don't give you the details of the path, it must be conservative, otherwise it's not even a reasonable question. So the potential energy due to this I calculate and work out like that. So this was a challenge question last year. And I think some people rose to the challenge and some didn't. I'm just telling you guys ahead of time, here's another problem I might ask on the test. So now you've seen it, it won't be a surprise to you if I ask it. So anyway, thanks guys.